Okay. Okay. So, good afternoon to everybody. I'm Calore, and in this presentation I will speak about the use of FPGAs, in particular in the context of using them as a computer accelerators. In this presentation, okay, I will start with a brief introduction about why I'm speaking about this topic and why I'm working on this topic. And then the main part of the presentation will be around the so-called FPGA empirical offline, which is a tool that we developed here in Ferrara in order to measure the performance of FPGAs when using them as computer accelerators. And then I will show some applications using FPGAs as accelerators, just to show how how they compare with other devices, other processors or other accelerators, just to convince you that they are actually working and they can be useful in some conditions. So, why are I working on this? In our group, we worked in the past, and we're still working on the so-called technology tracking inside NFM Ferrara. So the idea is that we are experimenting, we are analyzing the performance and benchmarking of novel hardware architectures. So in the past, we worked with Intel CPUs, with many cores, using also, let's say, strange kind of CPUs that did not get so popular, like Xeon Phi, but also with GPUs from NVIDIA, both high-end GPUs like the Tesla one, but also embedded ones in order to test for the energy efficiency, but also GPUs from AMD, or also CPUs with different architectures that are not Intel CPUs, such, for example, ARM CPUs, like the Thunder X2, and recently the Grace CPU from NVIDIA. But anyway, in this presentation, I will focus instead on FPGAs, which are another kind of processor, which are not CPUs, not GPUs. They are different kind of processor that can be, let's say, programmed in hardware. But I will get to it later on. So, actually, I started to work on using FPGA inside this project, which is called the RISE, which is a European project that aimed to use FPGAs as accelerators inside a supercomputer. Actually, the idea was to design and to build a prototype of a supercomputer using FPGAs. FPGAs were planned to be used as accelerators for the compute, so to compute, to actually to use as accelerators for the computations inside the machine, but also to be used as let's say network devices in order to communicate, to let different nodes of the computer or the supercomputer to communicate between them. Here, the idea, I don't know if it is clear to everybody, a supercomputer is just a lot of computers connected together. So the idea is that we need some devices to let the different compute nodes to speak to each other, to communicate between them. So FPGAs can be used also to do that. So another key point of this project was to be able to let the users of this computer to be able to program those devices using high-level languages. Here the idea is that we want to program FPGAs using, for example, the C language, as we are doing for CPUs, for example. In the past, FPGAs were programmed using specific languages that are, mastered mainly by people working in the electronics. And so for software programmers, software designers, it's not so easy to use those kind of devices. But this was true mainly in the past. But nowadays, we have also high-level languages that can be used to program them using, for example, C, which is something that the study developer should know quite well. So here is a rendering of one of the blades of this supercomputer, this prototype of the AeroX project. So here is instead a photo of the actual container that was used to install the prototype. So the idea is that inside this container we have different racks, and for in each rack we could host 32 AeroX blades. And in each blade, there were 16 CRDBs. Each CRDB, I will get into them in a couple of slides. Those are the nodes. So we have 16 different nodes inside one blade. The main idea is that you can imagine them to be 16 different computers installed in the same case, in the same blade. And then we could have multiple blades installed in the same rack, and then different racks connected together inside this container. Inside, so a CRDB is like a single computer where we have a CPU, which is actually an ARM architecture CPU, connected to a small FPGA that was used as a network device to speak with other compute nodes inside the blade. And then we have a big, let's say, or a bigger FPGA that is the actual compute accelerator inside this node. So the idea is that the single board is this one. So here we have the big FPGA, the compute accelerator, and here is the small one, which is the one that hosts the CPU, and the small FPGA uses the network communication. So here is a view of this board installed into the cooling system. The cooling system is a liquid cooling system. So here is the inlet of the liquid that is used to cool down the big FPGA, and this one for the CPU and the smaller one. So what's the point? The point is that what would be the first problem, or one problem that we faced, was that we needed to estimate the application's expected performance on this device in order to co-design the device itself. Okay, so the point is that this is a prototype. This was a prototype of a supercomputer, so we wanted to understand how fast an application could run on this kind of device. And also we wanted to understand which are the bottlenecks when running on such a device. So the point was that we needed to estimate the application performance, expected performance on this device before building it, and also we wanted to evaluate the device after being let's say, commissioned and run into operation. And actually, the main reason, I was working on this project as the leader of the work group that was in charge for the evaluation of this project. So the point was to try to understand how fast application could run on this, and which are the limits posed by this architecture to the performance of applications. So what is limiting the performance of applications in general? So here in this sketch, I have a CPU, but you can think it to be any kind of processor. So it could be a CPU, a GPU, an FPGA, whatever. The main idea is that in every compute system, we have two different subsystems. One is let's say the compute part, and the other one is the memory subsystem. So the idea is that our application could be limited by the amount of operations that we can perform per second, or otherwise it could also be limited by the bandwidth with the memory, so the amount of byte that we can read and write from the memory. So you can think it as a manufacturing system where you have a device that is able to build some items, an amount of items per second, but it can reach that kind of items per second only if we can provide enough material, let's say, to build those items. So the idea is the same. So we could be limited by one or two. So this is, let's say, a characteristic of the machine, of the hardware. On the other hand, we have an application. We have applications, different kind of applications. And for each application, or also for each, let's say, function of an application, you can think that that function, that algorithm, has some property, which is called the arithmetic intensity, which is the amount of operations, that of a mathematical operation or computation operation, that function or that program does per byte that it requires to read or write from the memory. So the idea is that we have some applications that needs to read and write a lot of bytes, and it requires to perform few operations per byte. Or on the other hand, we may have applications that require to perform a lot of computations, but they do not require to read and write a lot of bytes from the memory. So the idea is that we have the arithmetic intensity, which is a property of the software, of the application, and this one, which is flop versus flop per second versus byte from per second, which is a property of the hardware. So in 2009, in this publication, was proposed this model, which is called the roofline model, which is merging, let's say, the two different properties. So in this simple model, we have on the x-axis the operational intensity or arithmetic intensity of our application, while on the y-axis we have the performance that we can reach on a given machine. So the idea is that on this plot we have this roof line, which is given the name to this model, which is actually made by two different lines. This line is the peak performance given by the hardware architecture. So, for example, we may run on a processor which has a given maximum compute performance of a given flops per second. So, for example, this is the roof line, which is limiting our application performance, and it is given by the hardware. On the other hand, here we have another line which is related to the bandwidth. So this line is related to the maximum performance that we can reach on this architecture because of the memory bandwidth. So the idea is that when we have a given application or a given function inside an application has a specific operational intensity. So for an application, we can find a point on this axis, on the x-axis, which is given by the operational intensity. If this point is on the left from this point, we know that that application on that architecture is limited by the bandwidth. On the other hand, if the application is on the right from this point, we know that that application is limited by the compute capabilities of that architecture. So using this model, we can, given a given architecture, we can, also from a theoretical point of view, without running it, we can know if that application will be limited by the bandwidth or by the compute capabilities. Then, if we also try to run the application on the given architecture, we can measure the performance of a given application, and we can place a point on this model. And so we can also understand how far away is this point from the maximum theoretical performance. So in this way, we can have a view, let's say, of the expected performance of an application of a given architecture, and we can also know if the application can be further optimized in order to be closer to the actual offline. The problem is that this is not trivial to do for FPGAs. Because the point is that with CPUs or GPUs, you can draw quite easily, from a theoretical point of view, the roofline. Since you have a theoretical theoretical maximum performance and also theoretical maximum bandwidth that a CPU or a GPU can reach. The point is that a CPU or a GPU both of them have a quite specific number of, for example, floating point instruction that they can execute per second, and they are working at a given, more or less, clock frequency. So it is quite easy to compute the maximum expected performance. While on FPGA, this is not trivial, since on FPGAs in general, we have, actually FPGAs are not like CPUs or GPUs already, let's say, built into a static hardware configuration. They are just let's say here I wrote like a bunch of hardware of different logic blocks that needs to be programmed by the user. So the idea is that here those logic blocks could be, for example, lookup tables, flip-flops, digital signal processors, and so on. So different logic parts that need to be programmed together in order to perform some kind of operation. So, for example, if we want to perform, let's say, an addition on the FPGA, we should, for example, select some of those logic blocks, connect them together in order to be able to read some bytes from the input, perform the addition, and then write, for example, the results on some output things. So I'm making it, this is simpler than it is actually is, but just to give you an idea. So the idea is that here we have some logic ports that needs to be connected together in order to perform some kind of operation. So the idea is that since we have generic resources to be connected together in order to perform some kind of operation, there are different ways to connect together to perform the same kind of operation. And also, we do not have a specific clock frequency, which is already determined for an FPGA. The idea is that the maximum clock frequency at which we can run the FPGA is given, for example, by the amount of resources that we are using, and also in particular by the length of the connection connecting all of the resources. The idea is that if the paths are longer, we cannot use, we need to reduce the clock frequency, since we have to take into account that there is some time required to propagate the information on the paths that are connecting the different logical resources. So we don't have a fixed clock frequency. So what have we done? What we did was to let's say start from what was already available. So for example, there were some tools like this one, so the Empirical Roofline tool, which was developed at the Berkeley lab, which is a tool that is able to compute the roofline plot for CPUs and GPUs. Starting from this, we developed another tool which is focused for, it is targeted to FPGA devices. It is able to compute the roofline plot for an FPGA. The point is that here, this tool, using HLS, which is a high-level language. So the idea is that I will show some pieces of the code, but the idea is that you can program it in C, and just adding some pragma directives, you can extract the compiler, let's say, to produce a configuration to be loaded into the FPGA. So the idea is that using this language, actually the kind of hardware resources that are used to implement a given operation, it is much more predictable. So in this way, we can actually estimate the maximum amount of operation that we can perform per second on the FPGA. So the main idea behind this tool is that to estimate the peak performance of the FPGA in terms of operation per second, we can assume that inside to perform a given operation, we require a given amount of resources, of hardware resources inside the FPGA. So, for example, to perform an addition, we require, for example, let's say 3 DSPs. To understand how many addition we can perform in parallel, we can take the whole amount of resources available, divide it by the amount that we require to perform just one operation, and so this is giving us the amount of hardware cores that we can implement to perform the same operation in parallel. So the idea is that if we multiply by the clock frequency, we can estimate to be able to perform that given amount of operation parallel for each clock cycle of the FPGA. So in this way, we can have a given amount of operation per second that the FPGA is able to compute. The problem, okay, the idea is that clearly inside the FPGA we have different kinds of resources, but in general we have one limiting resource to implement a given operation. So we can just, we can just take into account the limiting resource to understand which is the maximum performance, theoretical performance that we can reach. The point is that such kind of models were already available in the literature, and actually at the beginning of the project we started to use this kind of theoretical model without needing the benchmark that we implemented. The point is that, as was made quite clear in this Intel white paper in 2017, those kind of computations, those kind of estimations are not actually very precise. And the actual peak performance that can be obtained by applications is much lower than the one that you can compute using this simple model. So why is it happening? The point is that in that model, we made two optimistic assumptions. The first one, that we are able to exploit all of the available resources, and the other one is that we expected to be able to run each hardware, to run all of the design in the FPGA at the same clock frequency that is declared to be the maximum frequency at which we can run each resource. So the point is that the manufacturer of the FPGAs are giving a maximum clock frequency at which you can run each of the resources. The point is that that's the maximum frequency for one of those resources. If you want to run a bigger design, the clock frequency must be reduced a lot. So that's the reason why we had to implement an actual benchmark, so some experimental benchmark to be able to run on those devices and to understand which was the maximum clock frequency and the maximum amount of resources that we could use. So the main idea behind the benchmark is that what we wanted to have was a given compute function, compute kernel, with an arithmetic intensity that could be configured by the user. So the idea is that to plot a roof line, we need an application with a configurable arithmetic intensity. So we can run it, we can, let's say, change the arithmetic intensity in order to experiment which is the maximum performance that we could reach at each point in the x-axis. Okay, so we can measure the roof line actually with different arithmetic intensity. So the idea is that here we are using HLS. So here this one is a plain actually not C code, since there is also a bit of C++, but anyway, let's say it's a plain C++ code. We just need to add some pragma directives, such as this one, in order to instruct the compiler, which is a compiler synthesizer, to produce some code that can be run, that can be installed into the FPGA. So here the idea is that we have just three functions. The first one is reading the input buffer from the external memory, and it is filling a queue, a first in, first out queue. So the pragma data flow directive is just instructing the compiler about the fact that those three functions can be run completely independently from each other. So while the first one is filling the buffer, filling the queue, the second one, which is the compute function, read one element at a time, and is computing some kind of operations. So now we will see later which kind of operations. Actually, could compute any kind of operation that we choose. Then we have the third function, which is just reading from the output queue and storing the results in memory. So running this benchmark, we can estimate the maximum bandwidth that we can have in the external memory, and we can estimate also the maximum amount of compute operations that can be performed inside the FPGA. So inside the compute function, we have just a few nested loops, let's say. So we have the first loop is just running through the buffer that we have in memory, reading one element at a time, where each element is actually a vector of few elements. This is mainly due to the fact that to reach the maximum bandwidth with the memory, we need to read, we cannot read just one element, but we have to fill, since the bus with the memory is made of parallel, let's say, lines, different paths from the, it is a bus, so we need to read a few elements in order to fill it and to reach the maximum bandwidth. So here we are reading a vector of elements. For each vector of elements, which is this one, what we are doing is we are performing a given number of operations. So here the op can be anything, it can be a sum, multiplication, and also some more complicated operations. And here we can, the main point of this code is that we are exposing to the user some knobs that the user can use to change the computational intensity of this code. So the idea is that we can change the length of the vector, so the elements that are read at each clock cycle, the number of operations that are performed on each element of the vector, and this initiation interval, which is the number of clock cycles that we are waiting before reading a new element. So if this is 1, it means that we are reading a new vector of elements for each clock cycle. So in this way, changing those variables, we can select the computational intensity of our code. And for example, to make it easier, changing this, which is the amount of operations that we perform for each element, we can clearly change the computational intensity of this code. Clearly here we could, from the software point of view, we can choose any combinations of those values. But on the other side, if we want to run this on an actual FPGA, clearly we are limited by the amount of hardware resources that we have inside the FPGA. So here we could ask to have thousands of different multipliers that works in parallel for each clock cycle, but then we also have to face the amount of resources that are available inside the FPGA. So we are limited by the amount of resources clearly. So we have to select, there are some combinations that are usable and others which are not. this is given mainly by the amount of hardware cores that we are able to implement inside FPGA. So we run this benchmark on this device, which is an Alveo from Xilinx, an Alveo board, which inside has an FPGA. And this FPGA is actually divided in 4 different SLRs, which are the super logic regions, which are just, you can think about them to be just independent FPGAs which can communicate in some way. So the idea is more or less the same that you have with the CPU cores. So they are different compute devices that are attached in the same package, in the same silicon package. The point clearly is that they cannot produce a single bigger one, so they just stack more of them inside the same package. So in this device, from a theoretical point of view, using the first simple model, we should be able to compute 1.45 teraflop per second, so floating point operations per second. Which kind of operations? Actually, in this implementation of the benchmark, we implemented as an operation an FMA, which is a fused multiply add. So it is a multiplication and an addition done at the same time with the same elements. Okay. The reason why we chose this one is that that is the operation that is commonly used to communicate to publicize the maximum performance that can be reached on CPUs and on GPUs. The reason is that that's the only operation that can be performed by a CPU or GPU in a single clock cycle, which accounts for 2 flops, since it is a sum plus a multiplication. So it counts for 2, but can be done in a single clock cycle. So that's the best operation to be done to estimate the performance on a CPU. So actually, this is, not very fair from the FPGA point of view, but it is fair from the CPU and GPU point of view. So that's the worst condition that we could choose for the FPGA. Okay, so this is from the theoretical point of view. But when we try to run that benchmark on that FPGA, on this FPGA, what we see is that while we increase the amount of resources, here actually I'm plotting just the DSP, which is the main resource that is used to implement floating point addition and multiplication. So that's the resource that is limiting the performance of this application on this FPGA. So the idea is that while we increase the amount of resources that we are using, we can see that the performance is increasing, but also that the clock frequency that we can reach is decreasing. So the point is that in this theoretical estimation, this frequency is completely, it is really too high. It cannot be reached in no way. Also using 5% of the DSPs, we cannot reach the frequency at all. On the other hand, here we are also taking into account that we are using all of the lookup tables and all of the DSPs that are available on this FPGA. On the other hand, here we can see that we cannot use more than, let's say, 85% of the DSPs. This means that we tried to do that, but the compiler cannot produce a bit stream that is able to run on this FPGA. So what we see is that, what we tried to do at first was to try to modify the theoretical model according to experimental results in order to have a more reliable model. And a more reliable model can be obtained using, in this case, for this FPGA, 300 megahertz for the clock frequency, and the possibility to use less than 70% of the lookup tables and less than 80% of DSP. So So this is a theoretical model that could give some better results, but clearly this is quite specific for this FPGA. So the benchmark to run experimental tests is needed anyway. So what we could do with this kind of benchmark, so what we can do is try to compare the performance of this FPGA with other devices. And actually we can compare, since the roofline model is something that is architectural agnostic, let's say, we can compare it also with other devices like CPUs and GPUs. So here is a plot. Here, I mean, we have the roofline of this FPGA, and then we have the rooflines of two different CPUs. This is an Intel CPU, this is an ARM CPU. And here we have a point, I mean, this is a matrix multiplication that is showing the performance that you could reach with an actual application. So this is an actual application that is a compute-bound application, and here you can see how close to the roof we can arrive. Okay, then we did it also for other FPGAs from Xilinx. So we could measure not only the external memory, but we could measure also the bandwidth of the internal memories that are inside the FPGA. But okay. Anyway, the point that I mean, someone also during a conference asked me, okay, why are you comparing the FPGA with CPUs and not with GPUs? Okay, clearly the reason is that a GPU could be much faster than this one. So why FPGAs could be useful if I mean we already have GPUs which are much faster. Okay, this plot is showing why they could be useful. The point is that if we're using, for example, double precision floating point operations, an FPGA, I mean, can reach a performance that is more or less the same of a CPU. On the other hand, when if we could use lower precision operations, we can reach a performance which is much higher. So, for example, this one is a single precision floating point. This is half precision floating point, and this is even a fixed. I mean, it is not a floating point operation. It is a fixed point operation. Then also we could reach higher performance using, for example, integer operations and so on. So the idea is that here this is the kind, let's say, of computations where FPGAs could be used. Okay, then what we could use them for? One of the kind of operations that where lower precision operations are required, even integer operation can be used, is, for example, the inference phase of machine learning algorithms, in particular deep neural networks algorithms. So here I will show you some slides. This is the first application that we see, where we show how we try to compare the performance that we can have also with other devices, not CPUs, but GPUs in this case. So the idea is that in the inference phase of the DNNs, we can lower the precision of the weights that are used to compute the inference. Also, in this case, the FPGAs could be programmed using different frameworks, different models. We could use the HLS as we did for the benchmark. But in this case, there is also an higher level approach, which is the one that we used in this case. So in this case, we use something that is called the PTCI, which is produced, distributed by the manufacturers of the FPGA, which is extreme, some configuration for the FPGA that is implementing all of the operations required to perform the inference on the FPGA. So the idea is that the configuration for the FPGA is already provided by the manufacturer. So the FPGA is the same that we used before. So again, it is divided in 4 different parts. and it is loaded with some kind of cores, let's say, that are able to perform in particular convolutions. So the idea, the tool is working in this way. So the idea is that you can use regular, tools that are commonly used in the field of neural networks, such as PyTorch, TensorFlow, and so on. Then the Xilinx is providing different tools that are able to take the model, for example, a trained model that is already trained using floating point 32 bits, and then is able to quantize the weight and produce the same model using integers with 8 bits, so lowering the precision of the weights. And then this can be compiled, let's say, in a sequence of operations that can be understood by this device, which is called the DPU. Okay, so as an application, we tested a segmentation, the segmentation of images from, let's say, a medical application. So the segmentation, the idea is that the application needs to find the calcium lesion inside the aortic valve. So in this application, or in this slide, we can see the results that we could obtain from an accuracy point of view. So the idea is that here are the original images. Here is the ground truth, so where the calcium is. Here is the prediction made by a GPU. And here are a couple of predictions made using two different, say, slightly different approaches, and not going too much into the details. Showing the prediction of the FPGA. So we compared the results obtained on our FPGA with two different GPUs. So this is a P100 GPU, which is the GPU of the two, that is made using the same technology, the same transistor technology as the FPGA. On the other hand, here we have a newer GPU, which is made with the newer technology. So this is expected to be faster, but it's also not so fair to compare them, since they are two different devices made with two different technologies. So here is the inference performance on those architectures. And so we can see, so here we're comparing both with the CPU and with the two different GPUs. So here is on the x-axis, you have the number of threads that are the CPU threads. So here on the CPU, clearly the performance is increasing with the increasing of threads. On the other hand, here is the yellow one is the FPGA. So in the FPGA, we have three different DPUs. So we can scale up to three different threads. So here is the performance that we can reach on the DPU, the maximum performance that we can reach on the DPU. This is the maximum performance that we can reach on the P100, so the GPU with the same architecture, the same technology. And this one is the V100, which is the GPU with the newer technology. So we can see that those are comparable between them. So that's quite a good result. This is even better from the energy point of view. So here is the CPU. Here is the blue one is the average power drained. The red one is the energy per image. And so you can see that concerning this is the FPGA, so the three different DPUs. So what you can see is that the power drain is lower, but the energy is lower, quite lower, both from comparing with the P100 and the V100. Okay, so just a couple of words. This is a work made, I'm speaking about it, but clearly it is a work that was made by different persons, different students. In particular, we are working in the group with Fabio, and Valentina Sisini, Giada, Minghini, and Miola worked on these specific implementations, and specific implementation and on producing the plots and results and so on. So then here we have also another application. And this application made mainly by Marco Reggiani and Stefano, is another application that is implementing the edit distance computation, which is, okay, this is not related to artificial intelligence. This is another kind of application. And just to show you that also other kind of application can run on FPGAs and can reach good performance. So this application and this, the edit distance is the number of operations required to morph a string S1 into a string S2 using three kind of operations. So these three kind of operations. And the idea is that it is used mainly when working with the DNA strings. So the idea is that if the cost of each operation is unitary, the corresponding, we can give a distance between two different strings, which is defined as the Levenshtein distance. So, it is easier to have a look to how it works. So the idea is that we have two different strings, for example, this one, A, C, A, G, and so on, and this one, G, T, A, C, etc. And the idea is that we want to compute a matrix that is it is telling to us how far away are the two different strings. So the idea is that to compute this kind of distance, we can use a low precision operations. And so this is a kind of operation that can be mapped quite easily on FPGA, quite easily from the performance point of view. It is not easy to implement it, maybe, but it is it is mapping very well on the kind of hardware that is available inside the FPGA. So the main idea is that inside the FPGA we can implement something which is called a systolic array. And the idea is that this, for example, those two yellow lines represent the first two strings. When we start to compute the first element in this diagonal, in this matrix, we can start to work on the first string, and then while we're still working on the first string, computing those two elements, we can start to work on another string, and so on. In this way, we can compute several strings in parallel, and clearly the limit on the performance is given by the amount of processing elements, so the amount of hardware cores that we can implement inside FPGA in order to let them work in parallel. So here are the results that we obtained. So the algorithm there are several, let's say, different algorithms that can be used to compute the distance. Here, the one that was used is the blended bias. So here we are comparing with two different results that are available in the literature. So here is what we obtain on the Albiol U50, which is another kind of FPGA, which is actually smaller than the U250 that we were speaking about before. And so this is the performance difference that we can achieve with respect to another FPGA with another implementation that is available in the literature running on another FPGA. On the other hand, here we have the same implementation that our implementation, let's say, running on the same FPGA compared with another implementation available in the literature running on a GPU. So also in this case, the performance is quite better on the FPGA. The reason why we have two different plots with two different performance for our implementation is due to the fact that to compare with other implementations available in the literature, we have to change, let's say, the length of the strings we are working on in order to work on the same length as the other implementations. Okay, so coming to the conclusions, the idea is that we can, nowadays, let's say, we can use FPGAs, we can program FPGAs using HLS, which is a high-level language. And so, actually, it's much easier to program them with respect to the past. And so also, let's say, software developers can start to try to use FPGAs as accelerators for their applications. The tools that are available to program them using HLS are getting mature in, say, in this moment in the history. So they are not completely mature, but they are ready to be used. And what we found, let's say, starting with them, I mean, our work is that using single precision, double precision, floating-point operations, FPGAs are competitive with CPUs. But to be competitive also with GPUs, it is required to use lower precision arithmetic. And so there are some kind of applications. So here in this presentation, I showed just a couple of them, which is the inference phase of deep neural network algorithms, and for example, the distance computation. So there are some specific use cases in which FPGAs can be better, can run at better performance with respect to other processors. The idea in general is that it is not, I mean, they are not limited to those use cases, but in general, when the lower precision can be used and they could reach high performance, but also they could be very useful when there is a requirement on the latency predictability of the results. So the idea is that FPGAs are working, we can precisely know at which clock cycle the results will be available. So this is something that with CPUs and GPUs, it is not so predictable. So, for example, they are used a lot in, for example, data acquisition systems, for example, in experimental physics and so on, for this reason. Using HLS, they could be used also by software developers to implement, for example, data acquisition systems. Okay, as future works, what we plan to do in the future is to try the same applications on newer FPGAs, and we already have some new devices that are available on the market. We would like to test a newer version of the other BTC tools, which are the tools that the manufacturers are providing to compile, to synthesize the code on FPGAs. And we also would like to test the performance and programmability of different tools, which are not provided by the manufacturers, but are provided, let's say, by the community, such as, for example, HLS 2ML. And then also to try to port and implement other applications. And so that's, thank you.